Check, check. Yo, what's up, everyone? Welcome to week 40 of Chill Kernel Hacking for Fun. Welcome back. Yeah, this week's going to be pretty good. I have a major update in that I got things working from last time. So that's where we're going to start off today. Last time, I was running into a ton of different issues that I was having trouble explaining, and honestly, it wasn't the best stream. I was running into this assertion in the interrupt handler, and I was totally failing to understand that, and there were just a bunch of problems. But actually, I have since fixed them and got it working, which I'll show you now. Okay, why is it taking so long to build and run? All right, let me, all right, maybe I spoke too soon. What is going on here? Why is none of my, what the? Okay, that was suspiciously slow, but, okay, and here, yeah, just to show you how, like, the state I got things into, this is what it looks like when the multicore bringup is working and the basic scheduler implementation is working. I'm able to bring up 4 CPUs and then actually execute them. I'm pretty sure it's happening on the different cores, and right now we're only using cooperative multitasking, and so each of the programs is intentionally coded to use this yield system call, which triggers the process to be descheduled and allows another one to run. But this is what it looks like when it's working. So I'm going to explain that. I'm going to start off by explaining a bit of what I know about those issues I was having, and then we're going to jump into, finally, we're going to jump into the next section of the class. Maybe we'll answer these questions, but I'm excited to get started on this next section, which is called System Calls for Environment Creation. We're going to implement some system calls, which is always a fun day when we get to do that. So that'll be pretty cool. And yeah, let's get into it. So that is a rough agenda for today. This stuff is super big for some reason. I'm gonna make these frames a little bit smaller, maybe. All right, never mind. I guess I can't do that. Maybe I'll make these bigger. Okay, so right. So on the last stream, I was running into a lot of these assertions. I would try to, do my kind of basic like CPU bring up, and then I would run into this assertion failed with this eflags thing. What this is saying is it's asserting that the interrupt flag is not present. The interrupt flag on x86 controls whether the processor can receive external interrupts or whether we're set to ignore them. And we can control this. We can set eflags and remove the we can do this in a variety of ways. We can do this with instructions, and so we can use the I believe it's CLI instruction to disable interrupts, and then the STI instruction to re-enable interrupts. The other way to do this is manipulating the eflags register, I believe. And that's what, at least you can query this state by reading eflags, and there's this interrupt flag bit. So what we're saying is we're asserting that it's not set, right? Assert that it's not set. Meaning assert that interrupts are disabled. in the interrupt handler. And the course documentation actually talks about this, and I'll show you that in a second. But that's the situation. I was really confused as to what was going on. And I thought I had messed up my interrupt descriptor table, but actually that's not at all what happened. I was going through the code, and yeah, so here's me kind of potentially changing things with my interrupt descriptor table, but really comes down to this line. So this is the sched halt function. And so what was happening is in our scheduler, when there's nothing to run, the scheduler calls this sched halt function, which basically just triggers the halt instruction of the CPU. Let me try to bring up my Intel manual, which is kind of useful. I kind of assumed the halt instruction shuts down the machine, but I don't actually think that is what happens. I think it actually puts the machine into this kind of low power state. Did I miss it? Yeah. Stops instruction execution and places the processor in a halt state. An interrupt, debug exception, various things will resume execution, but by default it stops execution. And so it doesn't like turn off the computer or something like that. It halts execution. And I can show this here maybe. Right. So yeah, when it's time to call sched halt, which is what the scheduler does if there's nothing to run, then we basically just kind of bring things down. We exit out of any process page directory or virtual memory. We switch back to this pure kernel page directory. We atomically set some state on this CPU that we're in a halted state, release this lock, and then trigger this assembly that triggers the halt instruction. But critically, what it does, I've commented it out right now, but it actually does this STI instruction, which re-enables interrupts. And I think that's actually a bug. I think that was a bug in this course skeleton OS that I'm working with. I don't think it was meant to be enabled. And the reason I say that is because there is this particular line that says blah, 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 uncomment the STI instruction something, something, something. And so it's suggesting that this thing should be commented out. And then later on in exercise 13, we should re-enable it. But we're nowhere near there. I'm still up here in exercise like 6. And so I believe actually this is meant to be commented out. And also that would explain this assertion, because here's what's happening. In my basic, in this basic environment I was trying to run things in, I have my multi-core bringup working. And so all the CPUs are coming up. I'm trying to execute a very simple program. I'm pretty sure it was just the divide by 0 one. That's going to trigger a divide by 0, which the kernel is going to handle. It's going to destroy the task, and then it's going to drop into the scheduler to look for something else to run. The scheduler is going to have nothing else to run because there are no other tasks registered with the system. So we're going to trigger sched halt. We're going to come here, and this thing is going to be uncommented out because of the bug. For whatever reason, it's uncommented, so we're going to re-enable interrupts. Interrupts were actually, just as a bit of context, interrupts are originally disabled as the very, very, very first thing that happens in the bootloader. We disable interrupts and we never turn them back on. Yo, what's up, Ahmed? Let me link you. It's this MIT operating systems course. So we disable interrupts, and we literally never turn them on again so far. So this will be the first time that actually we are re-enabling interrupts. Due to this bug that I think the course skeleton OS has. The CPU enters a halt state. So that's what happened so far. So now the CPU is in a state where interrupts are actually enabled. Actually, what am I doing? I'm looking for trap. And then the question is so how does this assertion hit? This is the assertion. And what happens is there's actually timer interrupts enabled by this point. When I merged in the lab4 code, it added a bunch of stuff, but one thing it does, or like at least two things it does are it enables the lay pick, which is the local something interrupt controller, programmable local application. What is lay pick? The local advanced programmable interrupt controller. And part of what it does is it starts setting a timer, which is going to trigger timer interrupts. In addition to the lay pick, I've commented it out for now. I don't know what this is all about. We're enabling the pick, the regular programmable interrupt controller. And there's probably some reason we do this. I'm not sure if this is related yet, but anyway, we enable these things. So I believe we are actually having timer interrupts coming into the kernel. And what's going to happen is we're going to halt this, like basically all of the processors. They're going to hit this. They're all going to re-enable interrupts. And eventually a timer interrupt is going to come in and trigger our interrupt handling infrastructure. But specifically what's going to happen is we're not going to have the proper interrupt registered for the timer interrupt, because we only handle 5 different kinds of exceptions right now. And a timer, like the timer interrupt, is not going to be any of these. So what's going to happen is the CPU is going to convert that timer interrupt into a general protection fault, pretty sure. And that is what's going to erase a general protection fault, which is going to lead us back to the interrupt, like the core trap handler, which I'm trying to find. Why? Okay. Hello, trap. And that's going to lead us here. We're going to come down here, we're going to do whatever, and we're going to hit this assertion. And interrupts have been enabled by this thing, and so therefore this is going to fail the assertion. Let me even see if I can show this. So I'm going to put the STI back in, and I'm going to observe that hopefully it's going to trigger the assertion. Let's see. Yeah, we're doing a bunch of stuff, and we're now failing this assertion in the interrupt handler. But if I remove this STI, we are no longer going to be re-enabling interrupts as part of halting the CPU, which means when the timer interrupt comes back in, we are no longer going to fail this assertion. And we don't, and now we're running correctly, and we're actually handling, like we're no longer asserting, and we're actually handling all these tasks and switching between them. I'm not quite sure what this looks kind of like weird output, but we are handling this correctly, and then eventually reaching a state where all the tasks have finished, and then we have no runnable environments anymore, and the kernel comes to a halt. So that's the fix. We just for the moment, the kernel is not set up for a state where we can handle like the timer interrupts, and so we can't be re-enabling interrupts. So I think this is a bug. And one other thing that helps me understand this was reading a bit more through this course documentation. And learning a bit more about, because I didn't understand that assertion at all. But this explains it. I was reading through this. This helps me so in JOS and the OS that we're working with, there's this key simplification, which is that external device interrupts are always disabled when in the kernel. And that's kind of what they mean by what's meant by, in the bootloader, we disable it on the first instruction. And then we re-enable it when a CPU goes to sleep, basically. But that is just simply an invariant of this OS design. It's just that interrupts are always disabled when in the kernel, and that explains this assertion. It talks about we masked interrupts with the very first instruction of the bootloader, and so far we have never gotten around to re-enabling them, and that's what we're seeing here. Right, and so that was just also helpful context for understanding what's up with this assertion there. Okay, so with that, I think that's enough background context. I'm actually going to experiment with if this pick thing is necessary by pick init. I wonder, I think actually things should still run. Oh, interesting. But it looks like it did run successfully. So I'm pretty confident actually we can leave that thing in. I can get rid of... Oh, I definitely need to add this. This is extremely important. Fix. Don't actually I'm going to do this over here. Fix. Don't re-enable interrupts on sched halt. I believe this was a bug in JOS. The kernel is not currently set up to handle external interrupts in this. Or maybe this is a bug in JOS. The kernel is currently sets the lay pick up to send timer interrupts, but we don't. Wait a second. No, I think I can say this simply. I believe there's a bug in JOS. Currently this triggers an assertion in the interrupt handler, which requires interrupts to be disabled upon entering the kernel. In the current state, the lay pick is enabled, which will trigger timer interrupts. The IDT doesn't handle those yet, so it gets converted to a GP fault. Oh, oops, that's a comment. To a GP fault. We'll attempt to handle this, but interrupts are enabled, so we'll hit the assertion. Okay, cool. I'm actually gonna take off my hoodie. It's a bit warm. Okay. Get my lighting. Okay, so we don't need this anymore. We also don't. I'm still not totally sure about this, but the difference is that I was experimenting with setting this to 0 rather than 1. 1 sets the IDT entry to be a trap handler, and 0 sets it to be an interrupt handler, and interrupt handlers automatically disable interrupts as when the CPU handles them. But I was just playing around with this because I thought it might be the source of that assertion issue, but I don't actually think it is. I think it's actually right to declare all those as trap handlers because I believe the interrupt handler is more meant for actual device interrupts, and none of those are. Those are like a GP fault, page fault, divided by 0, which are a different kind of interrupt. They're just like kind of synchronously executing things. So, yeah, halted. I'm going to just delete this. And I'll keep this in. All right. Use 3 yield. Okay, maybe initialize with 3 yield programs. Okay, so now we have a kind of decent, like the branch is still actually pretty messy. I'm going to do the further cleanup work here. So I have this weird revert thing going on. I added the basic round robin scheduler support, but then that started causing issues because I actually had a bug. So I reverted it and then reverted the revert to effectively re-enable it. And the bug was actually added a null pointer dereference. So what I'm going to do is I'm going to drop these. Wait a sec, what? Yeah, wait a sec. Yeah, okay, I'm going to drop these and then fix this one up. I don't want any of these reverts, and I want this fix to be merged into the main commit. S6, basic round robin scheduler. Okay, and I had this kind of weird thing. I had this, it's like this while one for debugging, which I reverted. So I actually don't need either of these anymore. And yeah, then I was also experiencing some issues with the locking. Okay, what I'm going to do now is I'm going to git switch branch F. Was it? And git branch F. Reset branch name to start point, right? Yeah, so git branch F lab for oct6 debug. Oops. So now, yeah. So now we're on the lab 4 branch. Everything should still work. Good. And yeah, and I think we are in a pretty good state. Let's just review the history. So I merged into lab 4, fixed the merge error, fixed some bit rot, fixed this boot bug, fixed my own code, which had some bugs, implemented the exercises. You know, actually this thing can go up. Add locking. I think I did this fairly correctly. So that doesn't have to be a whip anymore. And that's actually exercise 5. That's 5. You know, this thing actually 1, 2, 3, 4, 5, 6. And this stuff probably can all get squashed. So I was originally trying to just run div 0 and run with env_run, but that triggered a bunch of the locking issues. So I actually kind of think interesting. This fix belongs way down here. That belongs in the in the area of like fixing bit rot and stuff like that. So I'm going to reorder that. And then I think all of this stuff can kind of get squashed into one commit, actually. I think I'm going to do that. Let's see. So now it just looks like this weird line. So I can edit this a little bit. 386 init. Primes. Okay, I don't need this, and I also don't need this. So I can amend into there. So now all we're doing is technically leaving this primes thing. Just out of curiosity, I actually don't know if I've run the prime. What is the primes? Yeah, what it does all this crazy IPC stuff that we don't support yet. So I'm clearly not going to be able to run that yet. So yeah, I'm going to make this non-whip use 3 Yule programs to test multi-core scheduling. All right, let's go. I think so. I just cleaned up my branch, and thankfully it is still working. So with that note, I'm going to take a timestamp and I'm going to take some timestamps. We're at, what's up, Mr. RC, the pain of OS dev. That's right. That is right. We're 28:05. 28:05. Finish. Git cleanup. Okay. And now we have this nice looking history. I can go ahead and delete October 6 debug. I can push. Oh my gosh, I can push up Streamlab 4. Oh, I'm trying to, no, push origin. Git push origin lab 4. Pushing to my, okay, nice. Let's get it. So I think we're ready to continue. Let's just move on. So, all right. So let's zoom back to where we were. Round robin scheduling. I did this already. I implemented round robin scheduling. Make sure to invoke scheduled in MP main. Let's just check. So MP main is the function that all the application processors run when they boot up, and then what they do is they try to grab the lock and then enter the scheduler. Modify this to create 3 more environments. Did that. Don't forget to modify syscall to dispatch sysyield. I did that also. That is right here. Or is it? Wait, what the hell? It actually kind of doesn't look like that. Okay, wait, what? Okay, that is crazy. Why? Oh, visual handler. It's like, what is going on? Why is the sys yield instruction working? Maybe it's not. Maybe. How is that possible? I could have sworn I did this. Sys yield? Sys yield, right? You just call it sched yield. Yo, Mr. RC, did you write an OS or have your own OS? Yeah, this thing is not working constantly. C print F. Okay, this is. Oh no, what is going on? So I could have sworn this was working, but now sysyield is called and we are hanging. Oh no. What? You know, this is crazy. I could have sworn I did this. Is it an October 27 debug? So if I actually just don't do anything here, huh? It actually does run, but I'm actually not. But so sysyield is getting called a bunch, but we're actually just not doing anything. Oh my god. So, what's up, Afnan? Yeah, I did, but gave up after the scheduler because it made me suffer so much. Yeah, I can see why you. I can see why. Yeah. Yeah, it's just a lot of suffering. A lot of suffering. This is. Yeah, so we're about to do some more suffering. But kind of the weird thing is, like, what is, like, what is even happening? How long have you been working on this? I mean, so first off, I am just doing this classwork. So it's not, I'm like, all I'm doing is just following this like classwork, right? So I've been doing that like since February of this year for 2 hours a week. So yeah, that's how much I've been putting into it. God, okay. The music's good though. Yeah. All right, maybe I simplify this a little bit and And rather than doing I see it took me 6 months to get until the scheduler too. Yeah, I don't know. Like, were you working on it a lot? Like, I feel like I would make a lot more progress if I was spending more than 2 hours a week on this, but I don't have more time than that, so yeah. Also, this multi-core stuff is making things is like kind of complicated. Okay, so now we're doing 2. You know what I kind of also want to just see if I have 1 CPU. I feel like I'm like deadlocking or something like that. So we are going to come back here. We're going to actually try to do this. Yeah, okay. I'm just doing FAFO. What is FAFO? I have no idea what that means. Or anything along the way. I see. Yeah, I think if I were like, I think the class is super critical for me. Yeah. Okay, so right. So I have 1 CPU, and if I enable the sys yield to actually work, it fully works. But as soon as I enable 2 CPUs, we hang, and it's probably due to some locking or something like this. So yeah, that's the question, what to do now. It's probably a deadlock. Yeah. So my instinct with, I guess, yeah, I'm just gonna follow my main instinct. My main instinct for debugging deadlocks is to enter the debugger and reproduce the hang in the debugger, and then break and look at the apropos threads, info threads. So yeah, so basically like my main instinct for debugging the deadlock, which usually works for these kinds of deadlocks, is that, like, at least with the deadlock, things are easy in that the system is just frozen. So you can look at it in a debugger and see like where things are just like stuck basically. And so that's what we're doing now. So I can break into the debugger and look at the threads. And we can see they're both stuck in schedule halt on 106. Really? No way. It must be here. So it would really seem like I guess I'm gonna add some more prints. Sched halt unlock pre post. Let's just get some more information about this to see the register values. I'm not really sure the register values are what I need right now. I think that's a bit too low level for me. Okay, honestly, I'm like not sure what to do actually. This is super weird because, okay, the other problem is that this is all concurrently accessing the console, and the console output is going to get super interleaved, is what we can very much expect here. Okay, sysyield called pre, post, sysyield called. So where are things hanging? That's what I want to know. But again, if we have one CPU, this is all super easy. So it's definitely some kind of concurrency bug. All right. I think, yeah, I just need to add a lot more prints at various places to understand what's happening. So we have, so right now I have so-called sysyield returned and sysyield called scheduled, which goes into the scheduler. I'm just going to add another scheduled, switching to env. Oh, okay. So what is in here again? An env ID. In 32. Switching to env. Env ID. Remaining in env ID. So scheduled. Halt. So I don't know, this interleaving output might break a lot of things and make things hard to understand. You know what, maybe I just need to, also I think I could simplify this by reducing the number of loops necessary to a more minimal number. Like, does 3 reproduce? I mean, probably does like 2 reproduce the issue? Yes, does 1 reproduce the issue? And 0 is going to do, it's not going to run anything, so that should like work probably, right? Okay. Yeah. So clearly the problem is with sched yield somehow. We're going to make this 1. We're going to reproduce the deadlock. And I'm just going to debug it. Okay. And then the question is, oh wait, did the music stop? That's so annoying. Okay. Okay. And the question is, where do I break? I want to break in sched yield probably. I think I also want to just like break in umain. So now I'm in sched yield just from the basic boot sequence. And I'm just gonna step through it. We're trying to find an environment. We're finding one. We're going to drop into it. And that's where we're not really going to be able to step further, really. But we're going to enter the first environment, basically. And what's going to happen is it's going to... Well, I'm just going to keep stepping. Okay. I accidentally hit a next, which just kept going further than I wanted to. So now we're switching to the second thread. And now that one is also... So now we're on the second CPU. That one is also doing scheduled. And what I want to do is I also want to break on handle syscall. Right? How is that? Okay, good. So now basically both of these CPUs are getting an environment to run, and they're going to run them. So the next major event that's going to happen is one of those is going to trigger the system call scheduled, and I'm not sure which one it will be. I'm just gonna hit continue and see. So now we're in thread 1 again, which kind of makes sense. It was like kind of going earlier, so it makes sense that that would actually handle this. And so, okay, syscall. So now, oh, wait, but now we're in thread 2 again. So now we're in thread 2 again. This is, I've never actually done, okay, so no, thread 1 is back in user space. Interesting. It didn't hit, it didn't hit the breakpoint in a way that I thought it would. So the thread 1 is back in user space. And now we're in thread 2, we're in system call. We're switching on the syscall number. Thread 1 hit breakpoint, 2 and hex. Okay, I'm getting very confused actually, because it seems like thread 1 is only now hitting the breakpoint on the start of the program, which doesn't make any sense because we saw it. thread 1 hit handle. So maybe, wait, does, are there syscalls made before main? Sysget env ID. That's what we're seeing, okay. Okay, so thread 1 hit sysget env ID pass through, and it's now hitting umain. Thread 2, I think, is still at sysget env ID, but it's somehow triggering next advanced things. Huh. Interesting. This like multi-threaded debugging is pretty interesting. I haven't done a ton of that before, actually. I'm just going to continue on some more. So thread 2 received sig trap. And now thread 2 is at sysget env ID, okay. And we can yeah. So what happens? What happens after here? So after we handle drop dispatch, then we hit back here, which is what we're seeing. Right, 237. Yeah. Then we drop back into the environment that unless we're no longer running, then we drop into the scheduler. But by default, we have a system call. We drop back into the process. That's actually pretty interesting. That just shows that we're doing cooperative multitasking. Because ordinarily, if we were doing preemptive multitasking, a system call would be an opportunity for the kernel to run someone else. But here we're seeing that we don't do that. We don't really give other tasks the opportunity to run unless the current task is not runnable. All right, so now thread 2 is hitting main. Thread 1 is also somewhere in user space running the program. And so what we're going to expect next is the sys yield, hopefully. I'm going to continue. Thread 1, I believe, is now handling the sys yield. So I'm going to do a step. And I'm a little bit confused at what I'm seeing. Yo, what's up, Nick's OS Discovery? Inspired to dump my current project and start working on a non-POSIX mini kernel. No clue about that. I mean, if you have no clue, I would start. Okay, so I'm gonna dump you my resources. But basically, I would recommend starting with Harvard CS61. It depends on, like, if that's too easy for you, then do something else. But Harvard CS61 seems like a really awesome class for getting into this. So now, system call number 0. What? Is that a C puts? Oh, is that because, oh, this is annoying. Okay, wait, so that's because these things are doing a C printf, which is implemented with like this like C puts syscall. So I'm not interested in that. I'm gonna continue. Continue. We're also system call 0. So what we're seeing is the threads are slowly making their way through the main. They're hitting the C printf. They're triggering the C put syscall. The next system call we should see is the sys yield. So now we're in thread 1. We're in syscall 10, and that looks more correct. Yeah, right. Yeah, 16.6. Yeah, that looks much more correct. So let's break sys yield. Okay, so now we're actually in the case. We're going to hit the sys yield. We're still in thread 1. We're actually in sys yield. We're going to drop into sched yield. And let's just see what happens. What's the state of this? So we only have 2 tasks. One is held by thread 1. One is held by thread 2. Both are runnable. But wait a sec. But what if one is already being run? How do we make sure? What if it's being run by another thing? We don't want to run it also on 2 CPUs at the same time. Oh, never choose an environment that's currently running. Shoot. Okay, I think... Yo, that's the mistake. What's up, Ismail? Damn, I think I'm actually doing that. I think I'm running the task on 2 separate CPUs at the same time. That's bad. I'm pretty sure that's what's happening because I'm going through here. Maybe? I'm going through all these things. I'm not finding anything. How many environments are there? Is it way too many to step through? Yeah, way too many. 1 to the 10. Okay. Wish I'd mark debugging skills on some of my projects. But man, like you gotta, I don't know, the way like I got to this point is by spending a ton of time debugging throughout my life. So, yeah. But at some point you might find it fun. You might start to find it fun. Okay, so we're looping over this massive ass list. Env running. Where is this referenced? So we set the state to running. Okay, so I mean, I'm not sure, I'm not totally sure this will fix it, but I think it might. Never choose an environment that's currently running. What I'm interested is, so we set the running thing before we start executing. I see. The process can have an interrupt, but that it's still running. When does something get changed? Like become non-running? So we initialize things to runnable. When we destroy one, it becomes free. There's some dying state. We set it to runable. If there's a context switch. I see. Okay, we are in this case we're about to run something, so we need to we're about to run like some kind of environment. We need to deschedule the current one and then mark this E as running. Okay, so let's go back to scheduled. Yo, what's up? I cannot pronounce your username, Jared Miasm G. Thank you for watching. Thanks. So we need to clearly change something here. So we need to look at all the envrooms, starting from the next one. If it is runnable and wait a sec. It can't be running and runnable. It can only be one or the other. So actually, I think actually this is we're only looking for runnable environments. Okay. So my suspicion is that we have these two processes. Right now we're on thread 1. And we're hitting the yield. No, wait, where are we? We're hitting the yield on thread 1, right? Yeah, on thread 1, we're hitting the yield. And we're hitting the scheduler. We're seeing that the second thread is not runnable because it's also running. So therefore, we're like looping through this entire super long list, which I will actually take the moment to make like way smaller because I'm gonna make it like 10 or something to make this a bit easier for debugging. Okay. And then what? Oops. Okay, and then now I'm still debugging this version. I'm gonna break on this line, on line 62. Shed.c62, and we hit it. Good. So that means we ran through the entire array. We did not find any other runnable environments. So we're just going to... Oh, what the hell? It's... Okay, what's end status of 3? 0, 1, 2, it's 3. Oh, what? Oh, wait, but I think that might be the bug, actually. Ah, okay, interesting. Let's see. So we have the whole array of environments. We have our two environments. Thread 1 is hitting the yield. Thread 2 is still executing. Thread 1 hits the yield, starts looking for another one to try. Goes through all of them, doesn't find anything. So it's like, okay, well, I guess we didn't find anything. But now what I'm saying is, if it's runnable, I think this should actually be an env running. Yeah, that's the mistake. So what was happening is, I'm supposed to actually check if it's still in the running state and then just drop right back into it. But actually what I'm currently doing which is a bug, is checking if it's runnable, and then dropping into it if it is, but it's not. So I'm going into schedule halt, which just kind of like basically kills, like it just stops the core for the moment, because I am not handling timer interrupts. It basically just drops and kills the CPU core. And my guess is that it's going to happen on both CPUs actually. So the first core dies basically. It's going to hit the halt and die. The second core it's running its stuff. It's going to hit the yield. It's also going to try to look for something else. And the state it's going to see is this one environment, which is still in the running state, because that's the state we left it in. We have also the thread 2 task, also in the running state. It's going to do the exact same thing. It's going to look through all of them. It's not going to find any runnable tasks. It's going to try to drop into itself, but due to the bug, it's not going to do that because the task is still in a running state and the check is currently looking for a runnable state and there's nothing runnable. So core 2 is also just going to hit here and die. So the fix is to change this to running. And so it wasn't actually a deadlock. It was just I was buggily like killing the CPU cores. Okay, that was kind of exciting actually. Let's try this again. I wonder what's gonna happen. Oh, assertion failed page. Okay, that's totally unrelated. That is totally unrelated. That's related to my env hack, which I guess the smallest number I can set is page size, which is 4096, which is not worth it. Okay, please work. I think that worked. No runnable environments, that's a great sign. Yeah, I think that actually did it. It's a little bit hard to read, but basically the important thing is that we don't hang anymore. Previously, we were just hanging. So now I'm gonna try with 4 CPUs, just out of curiosity. Halting, good. And I will try it with the third one back. And all of the console output is going to be trampling over each other and stuff, but what's important here is that we're actually hitting sched yield and then going into halt. I'm not actually seeing I'm looking for the print that we have here, like the switching to. I guess this might not really happen actually, but I'm looking for this remaining. I'm just gonna do an assert 0 maybe. Okay, so we're getting there, and that's kind of what I expect. It's like we're going to be hitting the yield. The process is going to be looking for anything else to run. It's not going to find anything because all the other ones are going to be running on other CPUs. So it's just going to drop back into itself. And it's good that we hit the assertion 0, which means it was happening. I just didn't quite see it in the output, but oh, remaining in, there we go, remaining in. And yeah, so now let's run it for real. So I'm gonna remove, I had this hack in that only ran it for 2 loops to just get a more minimal environment. So I'm gonna remove that. I'm going to, yeah, let's just run that. Sick. Okay guys, I think we actually did get that working. So I'm gonna take a timestamp note at timestamp, I don't know, what time is it? 1 hour, 1:10:40, fix multi-core scheduling, hang. Okay. All right, let's go and clean this up a little bit. So we don't need this, don't need this. I'm timestamping. I mean, yeah, the timestamps, I kind of have stopped doing the recaps because I kind of am being a little bit lazy, but I might include them in the description of the YouTube video or something like that. Or, I mean, what I would love to have is these YouTube chapters things, which are based off of timestamps you can include in the description, but for some reason I have not been able to get those working. Okay, so this is a bug fix, and I'm going to come over here and apply that to this commit. I'm going to amend this one, and this is, I don't know, I guess it's also exercise 6. So, okay, cool. Let's come back here. So don't forget to modify syscall to dispatch syscall. Right, so now we finally did that. You should see environments switching back and forth 5 times and terminating like below. Back in environment 1. Is that what we see? 0, 1, 2, 0, 1, 2, 0, 1, 2. So they kind of are like kind of in lock step, but not quite. That is interesting that this console output is so clean and not interleaved. I actually don't really know. Oh, I know why it is, because of the massive kernel lock. Okay, so the reason this output is not all interleaved is because the user space processes are executing concurrently, but anytime they make a syscall, they take a massive kernel lock. So there's only, the kernel is only in kind of like handling one system call at a time. So it's not like the kernel on 2 different cores is like jamming console messages at the console driver like at the same time. It's kind of just taking a lock, handling one, then another, then the other, and that's why it's so clean. Unlike before, I think I don't know, these console messages were all interleaved. Which I actually don't quite understand, because I think those should also have been within the kernel, which and should have been like non-concurrent, or like with the kernel lock. But whatever. This looks good to me. Okay. In your implementation, you should have called load cr3. Did I do that? Yes, I did that. Before and after the call, your code makes references to the variable e, the argument to end run. I mean, yeah. Was this where I spent all that time debugging the crazy? Maybe it was, I think, no, that was env free or env destroy. Upon loading the CO3, the addressing context used by the MMU is instantly changed. The virtual address, that's meaning, why can the pointer E be dereferenced both before and after the addressing switch? Because The answer is because this is referring to kernel memory, which is kept constant across all processes. Or actually, well, in this case, we're switching from, switching from one process to another, but in each process we have these consistent kernel mappings, and in particular, this is going to be a address on the stack, because it's a function call, and so that is going to be on a kernel stack, and that is constant across all environments. Whenever the kernel switches from one environment to another, it must ensure that old environment's registers are saved so they can be restored properly. Why and where does this happen? Okay, so when we switch from one to another, we must ensure that the old ones are saved so they can be restored. We need to do this because if we did not save them, then when we kind of transfer control to the new process, we're going to clobber all of those registers and permanently lose the state of the program. And we will literally just be unable to re-execute and resume execution of the first one because we literally just forgot all of the program's state. So it's important to save all of this register state. And this happens in the trap frame. And so what happens is it's actually in the trap entry. I mean, the CPU is partially responsible for it. So, but actually a lot of it is right here in the push AL instruction. So the program triggers a system call or has some kind of exception. But when the kernel switches from one environment, so this switching from one to another happens in response to a sched yield currently. So a process will be running, and then in order to switch, it needs to trigger a sched yield, which is going to trigger an exception, like a system call interrupt exception. As part of doing that, one of the first things that happens in exception handling is we manually trigger a push AL instruction, which pushes the state of the registers onto the stack. It pushes all of the general purpose registers onto the stack. I think push AD or something, push all general purpose registers, which are like this whole big list. And so that's actually where it happens. We push all these registers and we save them into this thing called the trap frame. And then we take this trap frame on the stack and we actually, right here, we dereference it. We dereference the pointer and save it into this environment structure, and that dereference causes a copy of the data, because this object, this like trap frame object pointing to, has a very kind of transient lifetime. We created it as part of entering the trap frame, but when we leave the interrupt and go back to user space, that's going to be destroyed. So we need to do a copy. That happens right here. And that's kind of how this saving thing happens, but just to walk it through completely. So we save the register state for each environment within this environment structure. And then as part of doing end run, what we do is pop trap frame. This is the function that happens when we want to drop in and start executing any arbitrary environment. What we do is we go find that trap frame state that we previously had copied in there, and we actually, as part of the maneuver of like entering and dropping back into user space, we point the stack pointer back at the trap frame and then do an iret, which then the iret is a special instruction which then causes the CPU to look at ESP and look at the structure that ESP is pointing to, and then reload execution based off of it. But actually, I'm seeing that it's the pop AL here. So this is actually the analog to the push AL from before. On the entry to the interrupt, we did a push AL to save all the registers on the stack. We copied that into the environment structure, and then now we're trying to execute a random environment. We take that saved stash of registers. We point the stack pointer back to point at the trap frame. We do a pop AL, which pops like all these things off of the stack and back into the registers, and then we drop back into user space. So that's specifically how that happens. Challenge: add a less trivial policy such as fixed priority, blah, 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 blah. I'm not gonna do that. I don't feel like doing that. This is actually the more interesting one though. The JAWS kernel does not allow applications to use the floating point unit because we don't save those registers. All we save are the general purpose registers. And so if a application actually did use the floating point registers, then they would get clobbered. And so you can try to use them, but as soon as you do a syscall, there's no guarantee that those registers are going to get preserved, and it's just not going to work. So this would be an interesting challenge, but I'm not going to do it. I'm just going to keep going with the class. I think it's time for a 20-second break, which I've been skipping. So let's take a moment. Okay. So with the remaining half an hour, let's get into it. So system calls for environment creation. So we're going totally into new territory, although your kernel is now capable. I actually did my git is all good and whatever. Yeah. All right, I'm going to actually delete this one too. And now we are just nicely in lab 4. Wow. Oh, okay, that didn't work for some reason. I'm not gonna stress about it. Okay. Although your kernel is now capable of running and switching between multiple user level environments, it's limited to running environments that the kernel initially set up. You will now implement the necessary system calls to allow user environments to create other user environments. Unix provides fork. Unix fork copies the entire address space of a process to create a new one. The only difference is their PIDs and parent IDs. And the parent fork returns the child's, while in the child fork returns 0. Or in the parent fork returns the child's. By default, each process gets its own private space, and neither process's modifications are visible to the other. You will provide a different, more primitive set of system calls for creating new environments. With these system calls, you will be able to implement a Unix-like fork in user space in addition to other styles. The new system calls are exofork. Okay, what's exofork? And this system call creates a new environment with an almost blank slate. Nothing is mapped, and it is not runnable. The new environment will have the same register state as the parent environment at the time that I exit for it. The parent exit fork will return the end of the newly created environment. And the child, it will return 0. Since the child starts out marked as not runnable, sys exit fork will not actually return in the child until the parent has explicitly allowed this by marking the child runnable using sys env set status. Sets the status to runnable. Wow, okay. So you can use it to just modify this thing. It's kind of like a setter. It's just like in OOP we have getters and setters. This is just like a cross. It's like a setter exposed by the kernel as a system call. Page alloc. Allocate a page of physical memory and map it at a given virtual address. Okay, this is kind of like mmap, I suppose. Allocate and map it at a current place. Copy a page mapping, not the contents of a page, from one environment's address space to another, leaving a memory sharing arrangement in place so that the new and old mappings both refer to the same page of physical memory. Okay, page mapping from one environment's space to another. Okay, so this is basically just doing shared memory. Okay, so both of these processes are going to have virtual memory mappings that map to the same physical memory. Okay, page unmap. Unmap a page mapped at a given place. Okay. For all of these that accept environment IDs, the kernel supports the convention that a value of 0 means the current environment. This convention is implemented in ID to env. We have provided a very primitive implementation of Unix fork in the test program dumb fork. This test program uses the above two system calls to create and run a child environment with a copy. The two environments switch back and forth using syscalls. The parent exits after 10 iterations, whereas the child exits after 20. Word, nice, okay. Implement the system call as described above. And make sure syscall calls them. You'll need to use various functions and pmapping and env, ID to env for now. Whenever you call this, pass 1 in the check perm. Be sure you check for any invalid system call arguments. Returning eval. Test your kernel with dumb fork. Okay, this is super exciting, and I'm just gonna try to do this. Let's start with exofork. I'll also clean up my workspace a little bit. Okay, we're gonna need a few files. We're gonna need trap.c. Do we have sys exofork? We do. We have all of this skeleton infrastructure. Must be inlined. Exercise for the reader. Why? Wait, what the hell? Int blah 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 blah. T syscall. Cool, thanks Ismail. Cool project. Don't understand, but I find it very educational. Yeah, like yeah. Oh, I'm glad you get some use out of it. I know it's pretty deep and detailed. But yeah, no, glad you find some use out of it. Oh, but no, wait, what the hell? I'm not looking in the kernel anymore even. Okay. I'm in the wrong place. Sys exofork. So create a new environment with an almost blank slate. Nothing is mapped. No, it's not runnable. Okay. Allocate a new environment. Return env ID of it or -0, less than 0. Okay. So env alloc. How do I use env alloc again? It's been a very long time. Parent ID. Okay, so the struct env and the parent ID is going to be the cur env ID because we're the parent, right? And int I guess child env ID, or maybe just new env ID. Except that the status, okay, but this initializes a bunch of stuff. So then we're gonna do new env ID, or wait, what the? Wait, so this allocates something, like puts it into the free list and just returns. So now if we want to actually env ID to env, new env ID, but also we need to be handling errors, right? So, okay, if env ID equals no free env, return no free env. What is this? This can return no mem. You know what I'm gonna do? I could just forward the error from the below thing. That might be easiest. That's going to handle all these cases basically. New env ID. So now I need to get, and how does this work again? We pass in this thing, and wait, what? Oh wait, I'm being very dumb. Okay, env alloc stores it in there, right? So and status, no, env, no, oh wait, okay, this is a double pointer. Okay, just set it to null just for some hygiene. Status equals env not runnable. Oops. But what is this? We have an explicitly not runnable state. We have free, dying, runnable, running, not runnable. Okay. And the register set is copied from the current environment, but tweaked. So this is actually kind of cool. So we're going to copy the trap frame from cur-env, actually, which is going to copy the register set, but we need to tweak this so sysexofork will appear to return 0. Interesting. Are there? So the general way we will do this is we're going to set the EAX register. I'm just going to go to handle syscall where it kind of does this. So here's, yeah, but we don't do this directly. We're just going to set the return. Although wait a sec. But we're not returning back into our process. I'm just going to take the moment to do this. tf dot regs dot EAX equals 0. Okay. Set is non-runnable. Clone parents register state, but make child appear to return 0 from syscall. Hey, what's up, Kamal? Thanks, Ismail, for sharing the resources. Yeah. I actually updated my top recommendation. I kind of said that a bit earlier, but I'm actually recommending specifically this Harvard CS61 class these days, because that seems like an awesome class. That's in the resources list, but I just thought I'd call it out specifically. Returns an env ID of new environment. Return new env ID. I believe this is correct. So that's cool. Let's go and add exo fork, sys exo fork. Exo fork. It's void and returns a. Okay. It's void. So that class does both, Ismail. It does OS programming, but it also starts you off like, it doesn't just throw you directly into it. It also gives you a bit of an introduction to C and some systems concepts, which is why I'm recommending it, because it can be a bit much to dive directly into like OS programming. Okay. So ret equals blah 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 blah. And we build. Let's take a look at our diff. So we're implementing this thing, and this doesn't seem too bad. Less than 0, return it. Otherwise, set it to not runnable and do some tweaking. Let's just go with it. Exercise 7. I'm going to stop with that. Implement sys exo fork. Okay. Let's keep it moving. Sys env set status. All right, finally we're doing some fun stuff. Sys set status. Set the env ID's env status to status, which must be env runnable. Okay, I'm just going to assert status equals env runnable, or status equals env not runnable. As a basic thing, put that close to the top. Return 0 on success, return 0, -0 on error. Errors are these two things. So time to find out env ID to env. Let's see how this thing works. We pass in the env ID, environment store, and check perm, and we get back an error code. Ret env ID to env with the env ID. Get the struct env null, and we're going to pass in a 1. And if ret less than 1, return ret. And then we're going to interpret that to mean it was successful. So now we can go ahead and set the status equals status. Okay, actually no, I see that I was incorrect. If so, we should not assert. We actually should do an if. If it's not runnable and return e inval. We'll do that nice and early. Then we'll do our main thing, and then we'll set the status. And we'll take a 20-second break. Just stand up and stretch. Okay. Man, this is fun. This is so much more fun than debugging these insane issues. Okay. So now we're going to sys set env status. Sys set env, what's it called? Env set status. And we're going to, it takes 2 arguments, right? Is that right? Just A1, A2, I think. A1, A2. So now what's up with the return? I guess, yeah, we just return that back to the call, or we return that back to user space, I guess. Okay. Let's take a look at the diff. If it's not runnable and if status is not runnable, if it's not and it's not eval, otherwise look it up. The one, if that didn't work, return it, otherwise set the status. Okay. Pull sys and set status. All right, let's keep going. Sys page outlook. Let's speed run all these system calls. Page outlook. Okay, what do I need to do? Allocate a page of memory and map it at VA with permission perm in the outer space of env_id. The page contents are set to 0. Page is already mapped at VA. That page is unmapped as a side effect. Oh wow, interesting. Okay, so we forcibly overwrite whatever's there. We get some perms. PTEU, PTE avail may or may not be set, but no other bits may be set. See PTE syscall. PTE syscall in inc.mu.h. Okay. Return. This is going to have all sorts of error conditions possible. Like, yeah, dealing with virtual memory always has this stuff. All right. So we need to hint. This function is a wrapper around page outlook and page insert. Most of the new code you write should be to check the parameters for correctness. If page insert fails, remember to free the page you allocated. Okay. I can already sense a go-to fail. So let's get pmap.c around for reference. But no other bits maybe so bad env if it doesn't exist or the caller doesn't have permission to change env_id. What? Who has permission? How do I judge a permission? How do I judge this permission thing? I don't really know. Does it talk about permission here? No? Okay. Eval VA is greater than equal to utop or it's not page aligned. Eval of perm is inappropriate. Okay, I'm just gonna copy this over here. So as always, I'm just gonna start off with doing these input validation checks, which are an easy way to start. I'm gonna start with the VA. Can I do this? I don't think I can directly do this comparison. Return inval, or can I? I actually thought it would complain about a pointer to integer cast. Yeah, exactly. So usually I need to do the uint pointer t cast. Or pointer t va this is my kind of dumb way to do this with the modulus, but there's probably some other bit shifting ways to do this, but I'm just going to do it like this. So the VA is greater than or equal to utop, fail, or if the VA, I always get kind of there's this vim surround thing. See, okay, no, I'm just gonna do it this way. So if this thing modulus page size is not equal to 0, return enval. Return enval if the perm. Okay. Enval. Return enval. Go to enval. Okay. Let's validate the permissions. If perm is inappropriate, see above. Yeah, it would. Would be worth unit testing probably eventually. Okay. Okay. U and P must be set. I'm just gonna do. Can I do bool? UP R set equals perm and PTU and perm and PTP. Can I do bool? I'm pretty sure. Yeah, type def booled. Okay. PR set. So, but no other bits are set. If not UP are set, or other bits are set equals 0, or other bits are set, go to inval, right? And then time to implement this. So, this is going to be something like if we have this perm bit mask. The dumbest way is just to check every single bit. That's stupid. The easiest way to do this might be something along the lines of take the bit mask, set available and W to 0, and then check if the whole thing is non-zero or is 0, because everything should be 0 except for those things. So I don't know how. So perm, I need to do I can make a copy. Wait, this is kind of annoying. I can make a copy of perm, set the those two bits to 0, and then check everything else. Is there any other way to do this? There's probably a much better way to do that, using like So if I have, for example, 0010, and I want to make sure that only this thing is set. What can I do? I can, okay, it's good. Something along the lines of crafting a bit mask out of these two. So that's one input. Maybe this would be an example of an illegal input. Yeah, this function is for allocating. I mean, so this is basically mmap. Like it's called page allocator, but it's basically allowing user space to exactly make a like a memory allocation. So let's say I make a bit mask out of these things that are valid, and then it would be nice to have some kind of bitwise operation. Just do some bitwise operation on these, on this thing and this thing. What if I do an XOR? It's been a long time since I've thought about XOR, but I think that might. What is an XOR again? XOR is exclusive for it returns 1 when either of them are 1 but not both, right? Why? Okay. Either of them are 1 but not both, right? So this would be 0, 0, 0, 0. This one would be 1, 0, 0, 0. But the thing is, it's allowed to have nothing. So if I make, yeah, I see. Okay, but so if I do this, this will result in 0, 0, 1, 0, which is actually an allowed input. Right. This is going to be something along the lines of perm XOR bit mask. It's like bit mask equals PTE available or PTEW, and it's gonna be like perm XOR bit mask equals bit mask. So that's actually allowed. Wait, so it's allowed. It's okay if it's the bit mask. It's also okay if it's 0. It's not okay if it's anything else. So the allowed. Okay, let's say there were 2 bits though. So let's say for example, the lowest 2 bits are permitted to be allowed. So I'm just going to, so we could pass in nothing, we could pass in the first, we could pass in the second, we could pass in both, and we could pass in an unallowed input. And if we AND it against the bit mask here, that's going to produce 0, 0, 1, 1, because they're both different. If we AND it against the bit mask here, it's going to produce 0, 0, 1, 0, And likewise over here, it's going to do 0, 0, 0, 1. And then over here, it's going to produce 0, 0, 0, 0. And then over here, it's going to produce 1, 0, 1, 1. We could also imagine it passes something valid to invalid. So we can do something clever. It's definitely an option to do the XOR. It's just a matter of what is okay on the output. So we can do that, and then it's okay if it equals the bit mask or equals any bit in the bit mask or equals 0. But that is it. So something along the lines of XOR output then is okay equals XOR equals 0 or XOR equals PT avail or XOR equals PT EW or XOR equals bit mask. A little bit verbose, but I think it's correct. Yeah. So if nothing is set, we get the bit mask exactly. If any of the bits in the bit mask are set, we will get those bits. Okay, I mean, with if more bits were allowed, this would get quite dicey because we would need to check every possible combination of bits, maybe. There might be an even simpler way of doing this, but I'm not quite seeing it at the moment. I mean, another way is just to kind of cut out the sections of the bitmap that we care about and compare those against 0. Which kind of works, but it's kind of cumbersome, and so I feel like this would be a bit more elegant. And yeah, so I think I will just quickly I'll quickly just code this. Other bits are set, so it's going to be bool, or no, it's going to be, I don't know, int, and then int. The bit mask. What's this complaining about? Oh. What? This should totally be okay, right? Make? Oh, did I? Oh. XOR is perm okay. If not UP are set or not is perm okay, return or go to inval. To do unit test this. Okay, because I'm not totally sure that's legit. UPR set is totally unreadable. Mandatory bits are set. And bit mask, it's like allowed bit mask perm XOR result. Okay. XOR result. Oops. Oh wait, what am I doing? Okay. Okay, 0 or PT or both. This is has no unallowed bits. It's kind of a has only allowed. No, yeah, has. I don't like this double negative, but whatever. Okay. Maybe just has allowed bits. All right, y'all. And with that, I'm gonna sign off for today. Thanks a lot for watching week 40 of kernel hacking. I'll take the moment to plug myself. Feel free to join the Discord if you feel like it. Feel free to like, comment, and subscribe to my channel if you enjoy what I'm doing. And thanks for watching. I'll see you next week. Cheers. Bye. Bye, Smell.